Hello everyone. Today we are going to discuss about the topic counter and sequential circuits from design of digital circuits. So before in previous class we had seen that our flip-flops, there are four types of flip-flop, that is SR, JK and D and T flip-flop. So we had seen about the flip-flop symbols and characteristics table, and then characteristics equation, and then excitation of the four types of flip-flops. And then today we are going to see about the counters. So counter is a device which stores the number of times in a particular event or a process has occurred, often in a relationship to a clock signal. So this is about counters, which can be categorized into two types. First one is asynchronous counters and another one is synchronous counter. So asynchronous counters is also called as a ripple counter, which is nothing but it's a flip-flop output serves as a source of triggering other flip-flop. So the input of the flip-flop is output of the other flip-flops. This is called asynchronous counters. And then synchronous counter is nothing but it is a input pulse are applied to all clock pulse inputs of all flip-flops. The change of state of particular flip-flop is dependent on the clock pulse on the present state of other flip-flops. So this is about synchronous and asynchronous type of counters. So we have seen about the synchronous counters. So for synchronous counter, all the flip-flops are using the same clock signal. That's why the output would change synchronously. So before going to design a counter, we have to know about some procedure to the design of synchronous counters. So which is follows. First step is draw the state diagram for a given problem, and then step 2 is obtain the present state and next state table for a state diagram, and step 3 is make the assignment for the present state next state table, and step 4 is a decide the type of memory element, that is decide the type of which types of flip-flop we have used, and then obtain the excitation table. Step 5 is the draw the excitation map and simplify the excitation function. And step 6 is a final one, that is draw the schematic diagram for a excitation function. This is the procedure to design a synchronous counters. So here we are going to design a mod 3 counter. So mod 3 counter is having a 3 state. So first our question is design a mod 3 counter. For this we have step by step procedure. So first step is draw the state diagram. So the name itself, it is a mod 3 counter. So we have a 3 states, that is A and B and C is the 3 states. So we are drawing the state diagram as like this. And second one is obtain the present state and next state table. So from the above state diagram, one can draw the present state next state table, that is in your present state A, B, C. These are the 3 individual states. The next state is A is traveled into B, and then B is traveled to C, and C is traveled again to A. So this is the present state next state table of the above state diagram. And third step is make the assignment for above state state table. So in your present state, that is A is nothing but in your present state, for a mod 3 counter it is 0 0, and then next state is A is 0 0, B is 0 1, C is 1 0. So we can avoid the 1 1. Why? Because it is a mod 3 counter, only 3 states we have used. So and then present state to next state is nothing but 0 0 to 0 1, and then 0 1 to 1 0, 1 0 to 0 0. This is the state assignment of the previous present state next state table. And step 4 is decide the type of memory element to obtain the excitation table. So although any one of our 4 flip-flops, that is we already explained that is SR, JK and then D and T flip-flop can be used. The selection of JK flip-flop will result in a simplified circuit for a synchronous counters. That's why we are using JK flip-flop for the synchronous counters design. So here the excitation table having Entries for flip-flop input J1 K1 and J0 K0 can be drawn from the above present state next state table. In the first row of the above table, for the flip-flop, two of the counters to change from present state to next state, that is Q1, small q1 is equal to 0 to next state Q1, capital Q1 is equal to 0. J1 K1 inputs required are 0D. For flip-flop 1 to change from Q0 to Q0, the J.K0 input required are 1D. So similarly, other entries are also made using the application table. So this excitation input are already shown in your JK flip-flop. So by using that flip-flop excitation input, we can design the mod 3 counter also. So next step is draw the excitation map and simplify the excitation function. So this excitation map for J1, K1, J0 and K0 input of the counter can be drawn by using the above function, that is present state and next state table of excitation input. So for the first J1 having the values 0 1 dd, so this is replicated in your first K map, that is 0 1 dd. So we can map the values, that is we can pair the values. So that's why J1 is equal to Q0, and then similarly other values are mapped. K1 is equal to 1 and J0 is equal to Q1 bar and K0 value is equal to 1. So this is our excitation map or K map, and this is the simplified expression for the mod 3 counter. By using these expressions, we can design a schematic diagram for mod 3 counter. This is about your mod 3 counter. So we are using two flip-flops. Flip-flop is nothing but a 1-bit storage device. So we are storing 2-bit. So that's why we are using two flip-flops. First flip-flop and second flip-flop are commonly having the clock pulse. So without clock pulse, the flip-flop cannot work. And then see here, K1 and K0, both the values are 1. So here we are mentioning that plus 5 volt. If it is a 0, it is a 0 volt, and then it is a 1, it is a 5 volts. That's why we are giving the flip-flop K0 and K1 input as 5 volt. And then input for J1 is Q0. So the output of the first flip-flop is given to the second flip-flop input for J1, and then second flip-flop inverse output is given to the first flip-flop input, that is given to the J0. So why? Because J0 is equal to Q1 bar. So that's why we are giving. So this is our schematic diagram for mod 3 counter. Hope you all understand about this mod 3 counter design. As same as mod 6 counters, it's having the 6 states. Suppose we are someone asking to design a mod 10 counter, means we have 10 states. So by using the 10 state, we are decide to use how many flip-flops we are using, and then based on that flip-flops we are entering in your variables. So this is about your counters. Thank you.